Hello all. We will work on some problems from section 15.7 again. Yeah, last time we did approximately half of this section, and it's quite a heavy section, and therefore I will go over more problems from here, and you will see the difficult part is really one of the difficult parts is to put things together in the integrals and then the graphs, what the solid look like. Okay, let's start with number 20. Let's see, number 20. Use a triple integral to find the volume of a given solid. Number 20, the solid enclosed by y equals to, let's call that the first surface, surface 1, y equals to x squared plus c squared, and the second surface is y equals to 8 minus x squared minus c squared. Okay, so this is a paraboloid that is opens in positive y direction. Like so, if I try to sketch it, let's say this is the y-axis. This is the y-axis here. Okay, it will be like this. If we think of this as y equals to r squared, and this is the r here, okay, and then for the second one, this is y equals to 8 minus r squared, so it will look like, let me use different pen, let me use this one, so it will look like approximately like this. If this is 8 here, it will look like this. Now imagine if then we revolve this around the y-axis, that will give us this intersection here. Can you imagine that? Okay, so our solid actually looks like a paraboloid, opens to the right for the first one and opens to the left for the second one. Now then, what is the domain? If we project the shadow of this solid on the xy plane, if we project it on the xy plane, that will be a disk, right? Notice that that will be our domain of integration later on in the outer two integrals. Okay, that will be a disk with what radius? Let's put them together. So this y equals to r squared equals to 8 minus r squared. So 2r squared equals to 8. So r equals to 2. Right? Divide by 2 and then do the square root. Okay. So I will choose a point on that domain. Let's say, what color should I use? Let me use light green then. Let's say I pick a point here and I shoot in the y direction. I will enter the solid. I will enter the solid from the S1, okay, and then gets out the solid on S2, okay. So first we need to set up the double integral for the outside. That's for the yellow color. Okay. Of dy dc dx. Now the outer two integrals will be the domain on xz plane. Okay, and then the inner integral will be just the come in from the first solid, which is x squared plus c squared, and then coming out from the second surface. I'm sorry, I should say the first surface, and then coming out from the second surface, which is 8 minus x squared minus y squared. Now for the outer two integrals, that will be from -2 to 2, right? And then for any x that I choose, I come from negative square root of 4 minus x squared to square root of 4 minus x squared. Okay, that's the setup. Now, how about to compute that? We can compute that long way, okay, but even though if you happen to remember, we can also compute that using what you call that? Some kind of cylindrical chord integrations, okay. But this time the x, instead of using xy becomes our r theta, we use xc now to be our r theta. Let's do it the regular way first. So I will do it this regular way. So this will be double integral from -2 to 2 from negative square root of 4 minus x squared to square root of 4 minus x squared. The inner integral, that will be just the difference, the length of the interval. That will be 8 minus x squared minus y squared minus x squared plus y. X squared plus c squared. It should be c here. This should be c here. dc dx, which will give us integral -2 to 2 integral negative square root of 4 minus x squared to square root of 4 minus x squared, 8 minus 2x squared minus 2z squared dc dx. I can factor the 2 out, right? I can factor the 2 out. So there is 2 integral from -2 to 2, the integral from negative square root of 4 minus x squared, square root of 4 minus x squared, 4 minus x squared minus c squared dc dx. Now I do the inner integral. That will give me 4c minus, you know what, let me do it this way. That will be 4 minus x squared times c minus 1/3 c cubed from negative square root of 4 minus x squared to square root of 4 minus x squared dx. Furthermore, when I plug that in, I get 2 times integral -2 to 2, 4 minus x squared times 2 square root of 4 minus x squared. You notice that we can actually utilize the fact that the function, the integrand, is an even function on interval which is opposite endpoints, right? We can actually use that. Minus 1/3 times 2 the cube of square root of 4 minus x squared dx. Okay, which simplifies to be, let me continue here, this simplifies to be 2 times integral -2 to 2 of 4 minus x squared to the power of 3 halves with 2 at the front minus 2/3 4 minus x squared to the power of 3/2 dx. That's 4/3. That's 8/3 integral -2 to 2 of 4 minus x squared to the power of 3/2 dx. Okay. Now and then, how do we do it from here? Should we do trig substitution? At u equals to 2 sine theta, so du equals to 2 cosine theta. What am I doing? X equals to, not u. X equals to 2 sine theta, so dx equals to 2 cosine theta d theta. Okay, so the endpoints, 2 equals to 2 sine theta implies the theta is 1. Sine theta is 1, theta equals to pi over 2, -2 for negative pi over 2. Right. I purposely use a smaller angle. Okay, I purposely use a smaller angle. You can use 3 pi over 2, but it will change the orientation, you know. Okay, then the integral now becomes 8 over 3 integral negative pi over 2 to pi over 2, 4 minus x squared, that becomes cosine theta cubed times 2 cosine theta d theta. Ooh, that's quite nasty, huh? Okay, so that's 8 over 3. I don't know what I'm getting myself into. So you know what? So this is 3 here. So multiply by 2 integral negative pi over 2 to pi over 2 of cosine to the 4th. Let me write it as cosine squared theta being squared d theta, and then I do half angle thingy, right? This is 1 plus cosine 2 theta over 2 squared d theta. That gives us 4 over 3 integral negative pi over 2 to pi over 2 of, no, I don't have, this one is incorrect, should be 2 theta, not cosine 2 square theta. So this will be 1 plus 2 cosine 2 theta plus cosine square 2 theta d theta. Is it okay? And then when I integrate that, I think I have issue with the third one, but I'll do it later. So this will be 4 over 3. I don't like with my organization. Let me move things around first. So let me move these here. Also move these here, so that my integration now I can the later part, just to gain more space. We'll shift this up. Okay, now let's go on. So this will be pi integral of 1 from negative pi over 2 to pi over 2. That's pi plus, How about cosine 2 theta? That's sine 2 theta from negative pi over 2 to pi over 2. I think that will be 0, huh? Right? But if we think about it, the graph of cosine, this is pi over 2. Oh yeah, that's right. Yeah, that will be 0 later on. Plus, now cosine squared 2 theta becomes 1 plus cosine 4 theta over 2 under integral from negative pi over 2 to pi over 2 d theta. Plus 1/2 pi plus 0. Okay, so 4 over 3 times 3 pi over 2, that will be 2 pi. Oh, that's a long integration, huh? That's if we need to do it that way. But if we look back, so that's the first way to do it. But let me offer you another way to do this. What I will do is I make it into cylindrical integration, but my x is still r cosine theta. Instead of y, I use c as my r sine theta. Okay, I do that substitution. So we will end up with triple integral, the radius from 0 to 2. The angle is from 0 to 2 pi. Okay, for this thing, for the domain. The two-dimensional domain xz plane. Okay, and then the inner integral becomes from r squared to 8 minus r squared d c r dr d theta. That will be, it's in r dr d theta. No, actually r d theta dr. Okay, so that will be integral from 0 to 2, integral from 0 to 2 pi, 8 minus r squared r d theta dr. Okay, independent of theta, that's just 2 pi, the length of the interval, integral from 0 to 2, 8r minus 2r cubed dr. Okay, integrating further, that's 2 pi, that's 4r squared minus 2 over 4r to the 4 from 0 to 2. That will be 16 minus 8. Am I making a mistake somewhere? So why I get something totally different there? So 8, that becomes 16. So 1/2 of 16, that's 8. So that gave me 16 pi. Why is it so very different answers? My substitution. I forgot my tools. No wonder. I forgot my tools. Okay, sorry. So this will give me, I think that's the reason. So this should be 2 cubed here, right? So I have 2 cubed here. That's times 8 times 8 times 8 times 8 times 8 times 8. That's our 16 pi. Good thing I checked, huh? Otherwise I missed that thing. Yeah. Okay, so you see, if you apply the regular technique of integration, that will be quite painful. But once we are able to convert that to cylindrical triple integrals, that will be a lot easier. Okay, which we will learn actually in 15.8. Okay, but I basically reteach you here. Just use it here so that you see how convenient it can be. Okay, that's for number 20. Let's go on to number 22. you'll see the difficult part is actually not with the integrals. Yes, I did make a mistake, but that's a silly mistake though. Okay, number 22. The solid enclosed by the cylinder x squared plus c squared equals to 4. Oh, the same thing, huh? Similar to what we have earlier. Number 22, with the first surface is x squared plus c squared equals to 4. Notice that this is a cylinder parallel to the y-axis. Maybe I killed that a little bit. So that is a cylinder parallel to the y-axis. Okay, with radius 2, and then the second surface is, and solid enclosed by that cylinder, and planes y equals to -1 and y plus c equals to 4. So S2A is y equals to -1, and another one is y plus c equals to 4 or 2. I forgot. 4. Okay, so imagine that this solid is bounded below or on the left by y equals to -1. In some sense, that gives us the domain, huh? Okay, and then bounded above on the right by y plus c equals to 4. So imagine you have a plane cutting this way. So it gives us this cut. Maybe I make it thicker to help me. So that's what it looks like. Okay, on the YC plane, if this is y, this is c, y plus c equals to 4, right? Y plus c equals to 4. That's what this plane cutting. Okay, let me erase the parts that's not relevant. Okay, now let's start then. If we take a look on the quote-unquote two-dimensional domain of integration, the one quite natural one is the XC plane. That's a disk with radius 2 again, right? That's a disk with radius 2. So double integral -2 to 2 negative square root of 4 minus x squared to square root of 4 minus x squared, and the y will be from -1 to 4 minus z. Okay, that's the volume. I think I need to write that also up there. This is what the volume is. Now the first integral, the innermost integral, -2 to 2 integral negative square root of 4 minus x squared to square root of 4 minus x squared, 4 minus z minus 1, minus -1, sorry. dz dx. So this is integral -2 to 2 integral negative square root of 4 minus x squared to square root of 4 minus x squared. I get 5 minus z dz dx. Okay. Now you will see that this part actually becomes 0. You see, it's an odd function with symmetric endpoints, right? For the c component later on will cancel, but let's do it anyway. So this will be integral -2 to 2, okay, 5z minus 1/2 c squared from -4 minus x squared to √4 minus x squared dx, which will be integral -2 to 2, that's 5 times 2 √4 minus x squared minus 1/2 times 4 minus x squared minus 4 minus x squared. That's where the 0 comes. Okay, so we get now integral -2 to 2 of 10 √4 minus x squared dx. Okay, and this is equals to 10 times, I want you to think a little bit. This integral here, this is the area of semicircle with radius 2, right? Think about that. That is from -2 to 2, right? Okay, so we can say that, let me change back. So this is equals to 1/2 pi r squared. That gives us 20 pi. Okay, that's the volume. Which another thing is, if you think about this, we can easily, from this point here, change it into cylinder to polar integration. Okay, which is basically what happened also. If we think about that, that's what happened here. We change this into, if we change this into polar integration, this is what we get. Okay, if I come back here, this becomes integral from 0 to 2 pi, integral from 0 to 2 of r minus, what is my z again? R sine theta, right? R dr d theta, right? Okay, now that will give us, let me split the integral first. Integral from 0 to 2 pi, integral from 0 to 2 of 5r dr d theta minus integral from 0 to 2 pi, integral from 0 to 2 of r squared sine theta d theta, dr d theta. Now, this integral becomes 2 pi times r over 2, 5 over 2r squared from 0 to 2 times, minus, you will see this guy here is integral from 0 to 2 pi of sine theta d theta, because it's separable, right? Times integral from 0 to 2 of r squared dr. Now, this part will give us the 0. This part will give us the 0. Okay? And this part here will give us the 20 pi, as we expect. I think converting it into polar will be a lot easier. Okay, instead of doing the long way, the way I did here, and that's why you see I make a mistake, right? Okay, Now that's for number 22. Let's go on. Let me tell you again, remind you that one of the hardest part for this section is how to imagine that in how to imagine the graph, the solid, and translate it into triple integrals. And now we're gonna come from triple integrals and then imagine what the solid look like. Okay, now for that reason, I will do two problems here. Number 27, integral from 0 to 1, integral from 0 to 1 minus x, integral from 0 to 2 minus 2c, dy, dc, dx. Let's take the outer two integral first, which I usually call the domain of integration, right? The domain of integration which we express in double integral. Okay, so on the xc plane, this is x, this is c. The x will be from 0 to 1. The c will be from 1 to x, from 0 to 1 minus x. So that's what the outer integral look like. Okay, now then we will, from there, we will go for the y component will be from y equals to 0 to y equals to 1 minus 2 minus 2c. So on the y z, that will be so y equals to 2 minus 2c. When c equals to 0, the y is 2. When the c equals 0, the c equals to 0, the y is 2. When the y is 0, the c is 1. So that's what it looks like, huh? Okay, let's grab it in 3 dimensions. This is the x-axis. This is the yellow, the domain, yellow domain we talked about earlier. Okay, and you know what? Let's make it this way. That's the plane. This is the plane z equals to 1 minus x. Let me erase this yellow part. And let me use coloring this color here for this. And then it is being cut by that's y equals to 2 minus, see, can you imagine that? It looks like a pyramid now. I don't like this. Sorry, I erased too much. So this is the z equals to y minus x. And let me use this one. This is y equals to 2 minus 2z. Okay, that's the solid in the first octant. We know it is in the first octant because it is bounded this way here. Okay, that's for number 27. So imagine that it is cut by two planes in the first octant. Now the nice thing about these two planes is both of them are cylinders. Both of them are cylinders. So this one here is z equals to 1 minus x, and this guy here is y equals to 2 minus 2z. Okay, that's for number 27. Let's see number 28. Integral from 0 to 2, integral from 0 to 2 minus y, and then integral from 0 to 4 minus y squared, dx, dc, dy. Let's do the outer two integrals so that we get quote-unquote the domain of integration. The domain of integration is supposed to be xyz, right? But if I project it on yz plane, what will that look like? On yz plane, the y will be, how do I read that? The outer integral, variable of outer integral is y, so this is from y equals to 0 to y equals to 2. That's how we read it. Okay, so that's from 0 to 2. And then the z will be from 0 to 2 minus y. Okay, so this is quote-unquote the two-dimensional domain of integration for the outer integrals, the outer two integrals. Now, and then the x will be from x equals to 0 to x equals to 4 minus y squared. X 4 minus y squared. So that's what it looks like. But we just need the one in the first octant. So it actually looks like, if I extend from there, it looks like this. No, it's not. It's not. It is being cut. So it becomes like this. Not a good one. Like that. Where this part here, I don't like that. I try to color it in a way that I can refer to that later. So this part here is this. Okay, and the top, it is bounded by this guy. Okay, that's the top. Okay then, that's for this number 27 and number 28. To find the volume, of course, you can just integrate that, right? Okay, now let's go on. Number 30. Express the triple integral over solid E of f(xyz) dv as an iterated integral in 6 different ways. Dang, in 6 different ways. What 6 different ways? It refers to this order: dc, dy, dx, dc, dx, dy, dy, dc, dx, dy dx dz, and then dx dz dy dx dy dz. Okay, so those are the 6 order of integration possible from these triple integrals. Be very patient, okay? Be very patient. It's not easy, but we need to learn. We need to learn to visualize this anyway. Okay, let's start with number 30. Number 30. Do not attack the integrals right away. Try to sketch it first. Okay, so we have y squared plus c squared equals to 9. That is the circle on the YC plane, right? Okay, and then for x equals to -2 to x equals to 2. So let's copy paste that circle to the front and to the back. Okay, so if we take a look on YC plane, it is actually a disk, right? If we take a look on XY plane, think about this. On XY plane, if you project this cylinder shape on XY plane, it actually looks like a rectangle. Do you notice that? Right? It is actually looks like a rectangle from x equals to -2 to x equals to 2, and then the y come from -3 to 3. In fact, if we project that to XC plane, if we project that to XC plane, we see the same thing, huh? We see the same thing actually. We see the same thing. From -2 to 2, from -3 to 3. Okay. Now, why do we need these 3 projections onto XY plane, to XZ plane, to YZ plane? Because those will tell us the outer integrals. Okay, so for example, if I want to do the triple integral of f x y z dc dy dx, if I want to do that order first, okay, then dy dx, I need to look at this. Okay, the x will be from -2 to 2, the y will be from -3 to 3, and for each xy component coordinate that I choose, I will shoot from the bottom. I will hit square root of 9 minus y squared, negative square root of 9 minus y squared, up to integral up to square root of 9 minus y squared. Okay, so imagine if you pick a coordinate from here, let's say this coordinate. Okay, the z will move from the lower part of the cylinder, right? And coming out from that cylinder in the upper part of that cylinder. Okay, now using the same the same domain, if we reverse the order of integration to be dc dx dy, you will see it's quite similar. That's -3 to 3, -2 to 2, negative square root of 9 minus y squared, to square root of 9 minus y squared. Okay, so this part here is being used for two different triple integrals. Okay, let's go move on. What if I want to do the integral, triple integral of f x y z for dy dz dx? Notice that the outer two integrals is dz dx, means I need to look at this projection here. Okay, and that will be, x will be from -2 to 2, the z will be from -3 to 3, and then the y will be negative square root of 9 minus c squared to square root of 9 minus c squared. Imagine this xy plane. Let me make it thicker using dark color. This is my xy plane. I shoot from left hand side. I enter the cylinder on the negative part of the y and get out from that cylinder from the positive part of the same cylinder. Okay? Using the same notion, triple integral of f x y z of dy dx dc. Now using the same quote-unquote domain of integration, the outer two integrals, we get the z will be from -3 to 3, the y will be from -2 to 2, and then the dx will be from -2 to 2, and then y will be from negative square root of 9 minus c squared to square root of 9 minus c squared. Okay, we have 4 right now. Okay, be patient. What if we want to do triple integrals of f x y z of dx dc dy? So we look at this thing here now. Okay, the y will be from -3 to 3. Let me move that integral a bit to the left. The z will be from negative square root of 9 minus y squared to square root of 9 minus y squared. And x will be from -2 to 2. You will notice that if the outer two integrals are from the same plane, then the inner integral of those must be the same. Okay? With that said, then the last triple integral should be on the easy side, right? Should be on the easy side. That's integral -3 to 3, integral negative square root of 9 minus c squared to square root of 9 minus c squared, integral -2 to 2, f x y z dx dy dc. Okay, that's for number 30. That's for number 30. Ooh. How about number 32? This may be on the harder side. This may be on the harder side. X equals to 2, y equals to 2, c equals to 0, and x plus y minus 2c equals to 2. If I divide by 2, I wonder if you remember this technique. This to help us finding the x, y, z intercept. The x-intercept is 2, 0, 0, the y-intercept is 0, 0, 0, 2, 0, and then the c-intercept is 0, 0, -1. Oh wow, okay, so this is what the plane looks like. It's underneath. Oh. X equals, so this is 2 here, this is 2, this is -1. Z equals to 0, this is the xy plane. X equals to 2. What am I doing? X equals to 2 is here, and then the y equals to 2. I almost unable to imagine that. I think the point of view. I need to change the point of view. Let's do it this way then. Let me go ahead to xy plane. Xy plane. On xy plane we have x equals to 2, y equals to 2, and when z equals to 0, x plus y equals to 2. So we have x equals to 2, y equals to 2, and x plus y equals to 2. So we have this. Oh, no wonder I cannot imagine the solid earlier. So that's the xy plane projection. On xz plane projection, we have x equals to 2, z equals to 0, and then x minus 2z equals to 2. X equals to 2, z equals to 0. This is the c, this is 1. So that's what it looks like. So it refers to this part here. I definitely need more space. No, it doesn't look like that. Is it? X2, C, -1. Sorry, this is the wrong one. No, it doesn't look like this. The C should be -1. That part. I'm trying to imagine this honestly. You know what? I'm sorry. Let's do it this way. I don't like this. I don't like this. So I don't like this. So should we just skip the question? No. That's not what I meant. What I think I will do is I will screenshot this part here and then make it in a new here. This way I don't need to get overwhelmed with number 30. I have a question with this part here though. I need to imagine what it looks like first. So x equals to 2. That's x equals to 2. Z equals to 0. And then x, it's x over 2 minus 1 equals to z. So that's what it looks like, right? Okay. The thing is, I don't know if it actually refers to this one here or this one here. or maybe somewhere else. Let me redraw it. I'm sorry, it takes me. To be honest with you, I'm a bit confused. So this is C, this is X, this is 2, -1. Okay, but I don't know which part to shape. Let's see the YC plane. YC plane, maybe the same case though. So this is Y, this is C. Yeah, we have the same situation. So in 3 dimensions, what will that be then? X equals to 2, the Y equals to 2, and then X plus Y equals to 2. So this is X, Y, C. If these are my 2 planes here, it is cutting this way then. It's cutting this way. Oh dang, that's not easy to see. That's not easy to see. If I rotate this, let's try. If I rotate this, see it from behind, I don't need this line here. I actually get this one. That's what it looks like. That's what the solid looks like. That's what the solid looks like. Okay, at least we know what the projection on the ground look like. It looks like this, right? That one is not too hard. So triple integral of f x y z dc dy dx. X will be from 0 to 2. The y will be from this line here to y equals to 2. And then for any xy coordinate that we pick, it will come from z equals to 0, from c equals to 0 to the plane. 0 to the plane c equals to 2 minus x minus y over -2. Yeah, if we solve for c here, that will be 2 minus x minus y over -2. I think I prefer to say this is x plus y minus 2 over 2, huh? This, if we change the order of integrations, becomes dc dx dy. That will be from 0 to 2, 2 minus y to 2, from 0 to x plus y minus 2 over 2. Okay, so the xy plane is done. How about the xc plane? So dy dc dx. So if this is the x-axis, y-axis, and this is the z-axis, the projection of that will give us this part here. That's the projection. Okay? So x will be from 0 to 2. How about the y? The y will be from 0 to x, huh? Is it right? But then it will go into, for every coordinates I choose from that xz plane, it will go in the solid at that plane, x plus y minus 2z equals to 2 plane, and then get out from that y equals to 2. I hope you can imagine that. So I need to solve for y here. This will be 2 minus x plus 2z, goes up from solid at 2. Using the same concept, if I reverse the outer two integrals, the c will be from 0 to 2, the x will be from c to 2, right? Take a look here, take a look here. For this plane, if I go from, for any z I choose, I will get to the solid at x equals to c, and then gets out at x equals to 2, right? So go in from the solid x equals to c and gets out from x equals to 2. This will be 2 minus x plus 2z up to 2. Is it right? Why I feel like something not really right here with my graph? Because of this thing here. I just realized that too. I really need to step back here. I really need to step back here. I question my graph. I question my graph. Because this coordinate here, apparently if this is 2 and this is 2, this will be supposed to be 2, 2, 1. Right? So the C component is supposed to be 1. Yeah, if the C component should be 1, so something not right with my graph here. Here. Something not right with my graph. So this should be 2, 0, 1. So the slope is 1/2. This is from 2C. Yeah. So should be something look like this. I'm sorry, I kind of messed up on this question. Right? Let me redraw it so that we have better view. So on this side here, exactly on XC plane, we get 0 and then 2, 1. Right? The slope is C equals to 1/2 x. Right? So supposed to be, yeah. So we'll do correction. Instead of x, that's x over 2. Instead of z, is 2z here. Okay. Now, then on the left, on the other wall, the what do you call that? The YC wall, we will have this situation here. This is the YC wall. Okay, the YC wall, oops, too thick. It will be similar, huh? This is 2, this is 1, and that's what we get. Okay, so let me write it here. Integral, you know what? Let me move. Yeah, let me move. Let me move this guy here so that it's easier for us to see. So that's integral of f x y z dx dz dy. The y is from 0 to 2. The z will be from 0 to y over 2, and then from the plane, which is 2 minus y plus 2z up to 2. And then the last one, triple integral f of x, y, z dx, dy, dc. The c will be from 0 to 1, not 0 to 2. This is 0 to 1. And then from 2z to 2. And from 2 minus x plus 2z, minus y plus 2z up to 2. This is a hard one. I think one of the reasons why this triple integral is harder to work with is because the domain, the solid is not sticking to XC plane, not sticking to YC plane. It is sticking to XY plane. That's the pretty nice one. That's why it's easier for us to do the outer integral XY. Right? That one is on the easier side. Okay, but others are actually quite hard to do. Okay, now I show you how difficult this can be to emphasize that no, this part is not easy. Okay, it takes a lot of practice. Of course, I have to say that you need to get prepared anyway when it comes to the test, right? And I try my best to give you the type of questions, the type of solids that quite common. Okay, quite common and easier to get, but you still need to practice on this. Okay, you still need to practice on this. It's not easy. It takes a lot of practice, ability to see that in 3 dimensions. And I'm not ashamed, I'm not embarrassed to show you that I get confused. Okay, because it's common. It is common. Okay, get used to it. Get used to it, and don't be afraid to make mistake. Okay, but try to analyze that so that you can find your own mistake. The way I did. The further I try to analyze this solid, the further I realize, hey, you know what? It turns out that the coordinate here, originally I thought it's 2, 2, 2, and it's not, because the coordinate must satisfy that equation. Okay? Now, let's go on. Number 34. Number 34. The figure shows the region of integration for the integral. The good thing is they give us the solid, huh? the graph of the solid. Now rewrite this integral as an equivalent iterated integral in 5 other orders. Let's try to figure out first why they get this. Okay, so the outer 2 integral dx dc give us this. Okay, so when I try to sketch that, just try to confirm that that's the graph. Okay, my x is from 0 to 1, too far, 0 to 1, and my z will be from 0 to 1 minus x squared. So it's supposed to look like this, right? But we just take the first quadrant. Okay, this is the x, that's the y. So you see the xc give us this plane. So it's supposed to look like this plane originally. Okay, and then it is being cut by y equals to 1 minus x. So it's being cut by this plane. So imagine if you cut it by that plane, you get this intersection of that slanted plane and then the cylinder. Does it make sense right now? Okay. Now, let's erase those. I try to go over why we have that solid. Okay. But then, with that said, this is dc dx in the outer 2 integral. So if we reverse that, the f of x, y, z dy dx dz, so the c will be from 0 to 1, right? Okay, and the x will be from 0 to this part here. See, that's z equals to 1 minus x squared. I solve for x, so x equals to plus minus square root of 1 minus z, but I need the positive branch of that x. So we use x equals to square root of 1 minus z. As for the y component, for any coordinates I choose from this left wall here, I will start from 0 and then I go out from the plane. I go out from that plane, right? From 0 to 1 minus x. At least that's the one that we can cheat from. Okay. How about if we take a look on the ground, on xy plane? On xy plane, as you can see there, this is y equals to 1 minus x. Okay, so triple integral of f x y c dc dy dx, the x from 0 to 1, the y will be from 0 to 1 minus x, and the z will be from the ground to the cylinder, 1 minus x squared. Okay, likewise, if I reverse the outer 2 integral of f x y z dc dx dy, the y will be from 0 to 1, x will be from 0 to 1 minus y, the c will be from 0 to 1 minus x squared. I think that part is still quite easy. Notice that the yc plane is the hard one. The yc plane, the domain seems to be like a square actually, right? But if we project this this intersection down to the yc plane, we will get this shadow. We will get something looks like this. Okay, in which if I choose something from the coordinate from here, let's call this YC plane. Okay, if I choose the one below the parabola, then I will get out from that solid from that plane. Okay, so what happened is, let's call this the first region. The first region, and then the second region. Why? Because if your coordinate from XY plane is in the first region, you will come out from that plane. If you choose a coordinate from the second region, it will come up from that cylinder. Okay, so the triple integrals need to be divided into two parts. Okay, so triple integral in the first part of f x y c dx dz dy. For the first part, it will come from 0, get out from 1 minus z. I'm sorry, 1 minus y. Because it's dx, right? 1 minus y. Now, then the y will be from 0 to 1, but we need to find this intersection here. How do we find this intersection? This is the intersection of y equals to 1 minus x and z equals to 1 minus x squared. So x is 1 minus y, therefore the c equals to 1 minus y squared. Okay, so that's what the parabola looks like actually. The z will be from 0 to, what is this if we simplify this? This is 1 minus 2y plus y squared. That is 2y minus y squared. This is 2y minus y squared. Plus the second region, integral f x y z dx dz dy. If I start from the ground, I will go out from 1 minus x squared, the cylinder. The y will be from 0 to 1, and the z will be from 2y minus y squared up to 1. Okay, let me put a mark. This is the first region, and this is the second region. Okay, let's do the last part here. I know it's painful. Bear with me. Triple integral of the first region of f x y z dx dy dc plus double integral of the second region, integral of f x y z dx dy dc. Let me copy paste first. This will be 0 to 1 minus y. This will be from 0 to 1 minus x squared. Those two are easy because I copy paste from the last one. Okay, now in the first region, the z will be from 0 to 1, and the y will be, so if I choose a c, I go in at that parabola and gets out from 1. But what is that parabola? In y. What is this here? That's the intersection of y equals to 1 minus x and z equals to 1 minus x squared. But I need to rewrite that as y as a function of z. Y as a function of z. So x squared equals to 1 minus z. I take the positive branch, is it right? So I get y equals to 1 minus square root of 1 minus z. Is it the positive fraction? No, I take the positive fraction. Just to do the matching. When z equals to 1, when z equals to 1, the y 1. When z equals to 0, when z equals to 0, I get y equals to 0. So yeah, that match. Okay, so going back here, this will be 1 minus square root of 1 minus z. This is 0 to 1. This is from 0 to 1 minus square root of 1 minus z. Dang, that's painful, huh? This is so effing painful. I'm sorry, so heavy. No, I said from the beginning, this part is a difficult one. It's just like first you need to see the solid, okay? And then you need to quantify that not only with numbers, but also with equations, you know? So yes, it's not easy, okay? Notice that I spent approximately 1.5 hours already here. Let's do more. How many more questions I need to do? Okay, number 36. Number 36. They give us a triple integral. We don't see the solid, unfortunately. So from this triple integral, we need to go see the solid. From that solid, then we re-express into the other 5 iterated integrals. Okay, let's see first. So the outer 2 integral dz dy, the y is from 0 to 1, and the c is from y to 1. Okay, now and then x will be from x equals to 0 to x equals to z. So x equals to 0 to x equals to z. Huh. Can you imagine this? So this part here is this. From x equals to 0 to x equals to c. So will that look like this? So we know this is the original YC plane. And this is too much. So yeah, I think that's what it will look like though. Yeah, that's what it will look like. Okay, let's rotate this first. So this is integral f x y z dx dy dc. The z from 0 to 1. The y will be from 0 to z, and this is from 0 to z as well. I'm sorry. Yeah, 0 to z. This is from 0 to y equals to c. This is from 0 to x equals to c. Now, if we take a look on what it looks like on the xc plane, it looks like this. Okay, this line here is x equals to c. This is 1, right? So that will be triple integral f x y z dy dc dx. X will be from 0 to 1, from x to 1, and then the y will be from 0 to this part here, from 0 to z. Can you imagine that? If I pick something from here, okay, and then I shoot to the positive y direction. I start from the xc plane, that's why I did 0 here, and I will end at this plane. Now that plane is c equals to y. Okay. The other order, we have integral f x y z dy dx dc. The c will be from 0 to 1, and then x will be from 0 to z. This is from 0 to z again. This one is x equals to c, this is y equals to z. The hard part is when you project that on the ground. If you project that on the ground, it looks like a rectangle, a square actually. It looks like a square, but it has two different parts. Okay, let's say this is x, this is y. Okay, this is the first region here, and this is the second region. Okay, in the first region, x will be from 0 to 1, the y will be from 0 to x, right? But then it will go into the solid from x equals to z plane and gets out at 1, plus integral f x y z. This is for the second region. The x will be from 0 to 1, the y will be from x to 1, and that will be from y equals to z to 1. Finally, if we want triple integral of fxyc dz dx dy the y will be from 0 to 1, the x will be from 0 to y, this is x to 1, this is 0 to, I'm sorry, that's for the first region, my bad. For the first region, it should be from y to 1, y to 1, 1. This is from 0 to y, this is y to 1. Okay, I kind of like go a bit faster because I know I'm a bit run out of time. That's for number 36. I don't think I'm gonna do all of this though here, even though I would really love to. Number 38. So instead of doing number 37, let me just do number 38. Just number 38. So triple integral over solid B, where B is the unit ball, of c cubed plus sine y plus 3 dv. Evaluate triple integrals using only geometric interpretation and symmetry. Notice that this solid B here is a unit ball. Okay, let me break it up first. This is triple integral B of c cubed dv plus triple integral over B of sine y dv plus triple integral over solid B of 3 dv. But the last part here will be 3 times the volume of B, which is 3 times 4 over 3 of pi r cubed. So that's 4 pi, right? Now I want to argue that the first 2 triple integrals will give us 0. Why? For the following reason. If you try to set it up, you will see that this c cube here is an odd function, right? And then the c component of that b will be bounded between negative square root of 1 minus x squared minus y squared to square root of 1 minus x squared minus y squared for the c component, which then later on will cancel. Okay, that will give us 0 here. Now likewise, the sine part of y, the y will be between square root of 1 minus x squared minus c squared, right? From the negative to the positive. And you will get, because sine is an odd function, that will be 0 also. Okay, this will be a lot easier to do once we work with, what's that? Cylindrical or spherical integrations. Okay, so this is also odd function. Sine is an odd function over a domain with symmetric endpoints, opposite endpoints. Let me go on. Number 46. Find the moment of inertia about z-axis of a solid cone z-axis of solid cone. Z is between square root of x squared plus y squared up to h. So the top is h, and the bottom is z equals to square root of x squared plus y squared. Now we need to find the domain of intersection first, right? The domain of intersection, if you project this down, it will give you a this with radius square root of h. Actually, no, with radius h, that's right. Okay, so the moment of inertia about z-axis, means the distance of that point from z-axis is x squared plus y squared under square root. Okay, so moment of inertia about z-axis is equal to triple integral over that solid, call that E, of x squared plus y squared. That's the distance squared of from the z-axis of the density k dv. Okay, this will be a triple integral from let me see, from negative h to h, square root of h squared minus x squared, negative square root of, this is positive now, h squared minus x squared. And then as for the cone, it goes in from square root of x squared plus y squared and gets out at h. You have x squared plus y squared k dz dy dx, which is a lot easier to do if we use polar integrations. Let me use polar integrations right now. This will be integral from 0 to 2 pi, integral from 0 to h, r d theta. Okay, as for the z, that will be r squared times h times k, integral from r to h. Okay, so independent of theta, so that's 2 pi integral from 0 to h, k r squared h minus r d theta. Maybe r cubed right away. Make it r cubed right away. So I save one step. No more d theta, sorry. So 2 pi k h over 4 r to the 4th minus 1/5 r to the 5th from 0 to h. So there will be h to the 5th 1/4 minus 1/5. That's 1 over 20. Okay, that's the moment of inertia with respect to about the z-axis. Yeah, moment of inertia is the distance square. Okay, moment with respect to an axis, the first moment, that's just the distance, but moment of inertia is distance squared. Okay, I was planning to do number 48, but I guess I will stop here and give myself a little break.